institutes and industrial actors, as well as organizations relevant for the stationary sector and hydrogen supply chain. The objectives of the project as such: 5,000 hours operation of a large fuel cell based on PowerCell technology. With this, we want to show an increase in tolerance of impurities of hydrogen. We also, with this, will reduce the total cost of operation with lower cost materials, will improve by modeling and increasing efficiency of the system as such. We also include economic and environmental studies to look into sustainable developments. And of course, these results will be disseminated in a campaign planned from the beginning of the project. So the specific activities we're having, we're looking into development of catalyst, membrane, MEA development. We do perform cell and stack testing in the project. This is linked to modeling, economic and environmental analysis. System improvements, of course, on the overall fuel cell system by PowerCell, and the 5,000 hours of validation or test of system will be done at VTT in Finland. Good. So that was a very brief introduction, and I'll already now hand over to Katie, who will present a study on industrial quality hydrogen, which was performed last year during the study. So that will be followed up with a panel discussion, and I assume Katie will introduce our panelists after her presentation. So thanks, and Katie, over to you.
All right, great stuff. So yes, as Anders said, I wanted to start this kind of webinar today with a little discussion about what actually is industrial quality hydrogen. So the main motivation for this is, as Anders said, the Cleaner project is going to try and demonstrate fuel cell systems operating with this industrial quality hydrogen. And we're also going to try and increase the tolerance of these fuel cells to various impurities that can be found in industrial quality hydrogen. But of course, this very easily leads to the question, what actually is industrial quality hydrogen? And this is not something that's really been specified at the moment. So we've performed a literature study to try and figure out actually what impurities are going to be present in this type of hydrogen and what are the concentrations. In addition, it's important to understand where in the value chain these impurities are going to be introduced into the hydrogen so we can understand how to maybe mitigate them if possible. And then, of course, another objective of the project is to look at how these impurities impact the fuel cell performance. But today I wanted to focus most of all on these first two questions. So as mentioned, we performed a literature study in the project. We looked at different points around the value chain. This literature study has already been performed. It's available on the Cleaner webpage, so you can go and read it if you'd like. But I wanted to just give a very brief overview of some of the key points today. So basically what we were looking at is different hydrogen production methods, different hydrogen storage methods, and different hydrogen transmission methods. And again, what type and quantity of impurities might these different points in the value chain actually bring into this industrial quality hydrogen? But to take a step back, first of all, I wanted to just give a brief overview of why hydrogen quality is important. So you can see that hydrogen in our kind of ideal future energy system is going to be used for quite a lot of different things. And the presence of impurities in the hydrogen can have a lot of impacts on these different end uses. So in particular, we find that impurities can decrease the lifetime of these end uses. They can decrease the efficiency, so increase the total operation costs, and also increase the emissions. In particular, if we're looking into hydrogen combustion, either in combustion engines or in boilers, things like carbon-based impurities can lead to a lot of CO2 emissions. Otherwise, things like carbon monoxide or sulfide impurities can lead to a loss of performance and lifetime when using things like fuel cells. So some of these losses can be recovered, but this is obviously depending quite heavily on the type and the concentration of impurities and the specific end use. So currently there are quite a lot of different quality standards for use of hydrogen in various applications. So I've just taken a little brief overview of this ISO 14687 standard, which is basically quantifying the overall hydrogen quality for various applications. So you can see these different grades at the top all have a different quality standard for different end uses. And the specific impurities are also quite variable between the quality standards. It's not necessarily linear, so you can see that obviously the lower quality standards have a higher amount of impurities acceptable, but this is not always the case. For instance, if we look at the CO impurities allowed for grade C and D, grade C has a higher overall quality standard, but grade D has a lower CO limit. So this just underscores that actually the different impurities can affect different applications in different ways. And so we really need to be able to understand both what types of impurities might be present and also how they can affect the performance of these different applications, so we can set good quality standards overall. So first of all, I wanted to just give a very brief overview of the kind of impurities that we found during hydrogen production. So here we looked at a couple of different hydrogen production techniques. First of all, electrolysis to produce green, low carbon hydrogen, and also steam methane reforming, which is kind of the most widely used technique for hydrogen production today. And we also looked at naturally occurring hydrogen, which is something that's actually gaining quite a lot of interest in industry. So it's quite relevant for the future value chain. So first of all, steam methane reforming. So as I mentioned, this is the most common hydrogen production method today. Depending on where you are, anything between 2/3 and around 90% of hydrogen is produced via steam methane reforming. So it's quite, simple reaction. This is supposed to be an H. I don't know why it manifested like this. But basically, methane is reacted with the steam to produce syngas, which is a mix of hydrogen, and this should say CO as well. This CO can then be further reacted with hydrogen to produce CO2 plus even more hydrogen here. So we're effectively just producing hydrogen from methane. If you take the gas from steam methane reforming, it has a hydrogen quality of around 94%. This is obviously not high enough to meet any of the quality standards that I mentioned a couple of slides ago. So we need to further purify it. Some of the key impurities from steam methane reforming are things like unreacted methane. We have some CO2, which is obviously a product of this water gas shift reaction. And then we have some smaller, like lower level impurities, things like CO that can be unreacted, and also nitrogen, which is often introduced during the purging stages. So all these different impurities can be further purified. Often we use a technique called pressure swing absorption. This is basically a way of removing a lot of the impurities present in the hydrogen. But the PSA reaction is kind of has a variable impact depending on the type of impurity present. So we find that with different absorption strengths of certain impurities, then the actual reduction in the amount of impurity in the hydrogen differs. So things like CO and nitrogen are the hardest to remove through pressure swing absorption. The PSA technique is very widely used nowadays, I would say. Its process parameters are really well understood, so it can be utilized very efficiently to produce good quality hydrogen. One of the key things to note, though, is that the less impurities you want in your hydrogen, actually the less hydrogen that's resulting from the reaction. So if we want to bring CO quantities below the ISO standard, below 0.2 ppm, we actually only get 75% of our hydrogen out of this reaction. So the total efficiency is relatively decreased if we want to go for high purity, and this is one of the reasons why it's quite expensive. So something that has to be considered. The next hydrogen production technique we looked at was actually hydrogen as an industrial byproduct. This is a byproduct from processes like the chlor-alkali process, the sodium chlorate production. And actually what we find is that water is the main impurity for these processes. Now you might think that something like the chlor-alkali process could introduce chlorine-based impurities into the hydrogen, This isn't necessarily the case because these have a high solubility in water, which means that when we use drying towers to remove the water from the hydrogen, actually the chloride is also removed from the hydrogen. So we end up mainly with things like nitrogen present, again from purging at startup and shutdown, and a little bit of residual water. So again, this process is quite well understood. We have a good overview of the different types of impurities that can be introduced, and therefore we can provide purification even when we need. The third method for hydrogen production that we looked at was electrolysis. Now, if we use kind of renewable electricity to power our electrolyzer, this can be a completely zero emission process. So it's something that we're very interested in kind of utilizing. And electrolysis is also great because it can produce very consistent high quality hydrogen up to this kind of 5.5 standard, where the main purification that needs to take place is drying. So as you can see in the electrolyzer, we put water into the electrolyzer where it's basically split to oxygen and hydrogen. And this can kind of lead you to what the key impurities in the hydrogen might be, which is mainly oxygen, which can cross over from the anode to the cathode. Now, as you probably know, the mixture of oxygen and hydrogen can be explosive in certain quantities. So this is very carefully monitored in electrolyzer plants, which means that we're unlikely to have very high levels of oxygen in our hydrogen just for these safety reasons. We can change our electrolyzer operation parameters to try and reduce the amount of oxygen crossing over, and therefore the hydrogen produced can be very high quality. In addition, we can have different types of electrolyzers that might have additional air coming in on the anode. This can lead to some nitrogen impurities in our hydrogen, but again, studies have shown that these are kind of below the limits within the ISO standards, so it's not necessarily needing any extra purification. The one purification step needed is more or less drying, so the hydrogen is dried after it comes out of the electrolyzer to remove any residual water. And those are basically the main ways of producing hydrogen that we have today. But also, as I mentioned, naturally occurring hydrogen is something that's gaining a lot of interest. So what we see is that naturally occurring hydrogen is produced from the reaction of iron-rich rocks with water under high pressure and temperature underground. It can also be produced through radioactive water splitting, but this iron-rich is called serpentization. This reaction is the most common way of producing naturally occurring hydrogen. We see that there's a lot of interest gained in actually utilizing this naturally occurring hydrogen. And you can see in this map on the right-hand side here that all these little points are discoveries of hydrogen of greater than 10% purity. So these are mostly discovered when looking for things like natural gas or oil, or water even, like digging wells, things like that. But the problem with a lot of these discoveries is that they're often either relatively low volume, so you can't really utilize them very well, or they're non-permanent, so you get some hydrogen coming out for a short amount of time before eventually stopping. And there's only really one source of naturally occurring hydrogen that's been utilized until now. And this is this source over here in Mali, which is actually the highest known purity source of hydrogen. It's 97.4% purity, and it's been utilized for, I think, around 15, 20 years to produce power for a small village in Mali. So this is used in a hydrogen combustion engine, which is then producing power. So the key impurities found in this specific well here were mainly nitrogen with low levels of CO and helium. But again, it's not quite pure enough for any of the standards that we saw earlier. So additional purification is needed. And this is a very common theme for naturally occurring hydrogen. It's very unlikely that we'll be able to directly utilize it without any further purification. So yeah, very interesting though. Next, I want to talk a little bit about hydrogen transmission. Here we looked at transmission in tankers. First of all, this is quite a simple transmission method because you can expect more or less that whatever you put into the tanker, you get out at the end. So it's quite simple. But also we looked into new and repurposed gas pipelines. So as we can see, any kind of large-scale utilization of hydrogen, either throughout Europe or globally, will involve a lot of transport of hydrogen from one location to another. What we see is that there's a hypothesized European hydrogen backbone that you can see in this image on the left, on the right here. And this is going to contain both newly built pipelines, around 40% newly built pipelines, in addition to around 60% repurposed natural gas pipelines. So this is quite interesting because you're going to get a mix of new and old pipelines. This can have certain implications or challenges, both with respect to quality. In addition, we can have challenges with respect to the materials integrity of these old pipelines. This is not something we've dived so deeply into, but of course, using hydrogen in old pipelines can lead to hydrogen embrittlement. And one of the factors that we looked into was perhaps if you add different types of gaseous inhibitors to stop the hydrogen embrittlement, these can of course affect the hydrogen quality. And one of the key gaseous inhibitors that people use is oxygen at around 100 ppm. So you can see that that's some relatively significant impurity that would be introduced to the pipeline in order to, first of all, utilize it. There are also a lot of open questions about using hydrogen in pipelines. So first of all, the question is actually what type of hydrogen should enter the pipelines? So there's been several hypothesized standards about the hydrogen entering the pipelines. 3 different standards have been proposed, something ranging from 98% up to 99.5 up to 99.97%. The required quality is often really just dependent on the types of producers that are in the system and the quality that they're producing, and also the end user application. So most applications don't need this 99.97% purity. This is more or less only for low temperature fuel cells. So what we can consider is that most applications would find a quality of around 99.5% acceptable. And this means that if you have a specific requirement to have hydrogen of a better quality, then maybe the end user can be responsible for that additional purification step. But this is not something that's been decided or anything like that. So there's a lot of open questions about what kind of quality we would want to enter the pipelines. There was a project called Hy4Heat, which looked at using hydrogen in boilers in people's homes, and they recommended a quality of around 98%, but you can see that there are quite a lot of carbon monoxide, sulfur impurities, so this is something that has to again be agreed upon, not been really defined very well yet. In addition, transporting the gas in pipelines will lower the quality. So you're not going to get out the quality of hydrogen that you first put into the pipeline. And this is something that you can kind of imagine after seeing this picture on the right here. So this is basically a pig which is used to clean gas pipelines. This is a picture of it after it's been in a pipeline. And you can really see all this kind of mud, I would say, that's present on the pig. And that just gives you an idea that the pipelines themselves are not really very clean in the first place. So although we can clean them with the pigs, not every single type of pipeline is actually piggable, which means that a lot of them will still have residual solids in there. In addition, we can have a lot of water in the pipelines, and we can have a lot of gaseous impurities as well. So obviously the natural gas that was previously transported, as well as other hydrocarbons, things like sulfur-based compounds, and also halogens. So a lot of different impurities can be introduced during the pipeline transmission. One of the key problems is there hasn't been a lot of research exactly testing what kind of impurities enter into the hydrogen after pipeline transmission. So there was one very nice paper from one of our panelists today, Thomas, and his group at HyCenter, and they found a really nice correlation between the pipeline age and the concentration of impurities that you can see in this graph on the right here. So basically, the younger the pipeline, the less impurities that are introduced into the hydrogen when it's being transported there. So you can see a nice linear correlation. Unfortunately, this is not always the case. There are other factors involved, so things like the location of the pipeline that can have different impacts, different impurities that are brought in to the pipeline based on the location, and also the type of things that were transported in it. So this just shows that actually there are significant impurities that can be introduced into the hydrogen. And this study found that a lot of these impurities are hydrocarbon-based. So for instance, propane was quite a significant impurity, but we do see a lot of other things at lower levels as well, around the ppb level. Yes. Also, there's not been too many studies, I would say, looking at how these impurities develop over time. So of course, we can imagine that these impurities will be present at the beginning of our pipeline transmission, but actually how do they develop, say 5, 10, 20 years into the future? That's a bit more unknown. And there's been kind of colloquial thoughts that actually certain impurities, certain strongly absorbing impurities can have a really, really long lifetime in the pipes. So for instance, in our last webinar, Udo Lubenow, he mentioned that actually certain odorants can take over 25 years to drop to levels below 1 ppm. So there needs to be a lot more studies, I think, to actually figure out what the lifetime of these impurities are in the pipeline and how the hydrogen quality will develop over time. So hopefully that's something we can maybe discuss in our panel, and hopefully some research organizations can look into this further. And of course, again, the question becomes, who is actually responsible for maintaining the quality in these pipelines? So if you put in 98%, we can imagine that the producers are responsible for the quality that comes into the pipeline. But we've found in this study, for instance, on the right, they found that we can maintain a quality of 98%, but a higher quality such as 99.97% would be really difficult to maintain in the pipeline. Ideally, we want our hydrogen network to be available for all producers and all users, but of course, producers of high quality hydrogen might be reluctant to put it into a pipeline that's operating on lower quality, and users of high quality hydrogen might also be reluctant to take hydrogen from a lower quality pipeline. So there's a lot of, again, uncertainty and open questions around the hydrogen quality throughout transmission. Next and finally, we also looked at different hydrogen storage methods. So we looked at things like hydrogen carriers and also storage underground in geological features. And this is actually really interesting because, of course, if we have a long network of different pipelines of hydrogen going throughout Europe, we also need long and short-term storage sites. So our network can be flexible and we can provide the demand when needed. There are a lot of different types of underground storage solution that have been investigated, anywhere ranging from, very high capacity long-term storage time in depleted reservoirs, down to kind of short-term, smaller volume storage in things like rock caverns. And there have been several projects that have kind of investigated whether there is the possibility to store hydrogen in these kind of underground features. One of these was the Hayaspray project, which our panelist Remco was heavily involved with, and they developed this hydrogen map that you can see on the right here, which identified possible storage locations throughout Europe. So you can see that there are quite a lot of storage locations only within Europe, and of course globally even more so. But there are several considerations that we need to make when we think about underground hydrogen storage. If we use things like depleted gas fields, there might be some residual gas in there because it's been previously used to store hydrocarbons. So these will be present in the hydrogen when it's removed. And these can take, again, a very long time to actually be extracted from the site. And therefore, in the beginning, we can maybe imagine that we might use lower quality hydrogen in these types of storage sites. In addition, not all of these types of storage sites have been proven to be gas tight. Particularly aquifers, these haven't necessarily had gas in them before, so we need to do certain analysis of each individual site to make sure that it's secure and that the gas will not just seep out, particularly when it's used for long-term storage. So these are kind of maybe some of the challenges or some of the things we need to think about with underground hydrogen storage. When it comes to quality specifically, we also have to think about the interaction of the hydrogen with the storage site itself. So I just wanted to put this little map of the geology of Europe that you see on the right here to emphasize that actually the rock type within Europe is very varied. So the exact nature of the rocks and the type of storage site is going to be very specific based on the actual location of the site. And this means that there will be different types of rock present, and potentially different impurities present. So for instance, we can see that if we have rock types like calcite, these can react with the hydrogen to produce things like methane and CO2. Other rock types like pyrite can lead to hydrogen sulfide, and carbonates can lead to methane. So these different types of reactions that might be present are highly dependent on the different types of rocks that will be in the sites. There are certain types of rocks that have been shown to be less reactive with hydrogen, things like sandstone, quartz, silicates. So maybe we can focus on using these types of storage sites. But of course, it's not just the main rock type that potentially can react. There are also going to be impurities or inclusions in the rocks that can then have side reactions with the hydrogen to produce impurities that we might not have thought would be there previously. So a lot more, I think, research and studies needs to take place to figure out which specific storage sites will be suitable for high quality hydrogen. In addition, there haven't been too many studies that tell us the exact amounts of these different types of impurities that can be expected in the hydrogen. So this is kind of an open question as well. So in addition, there's not just rocks in the storage site, there's also going to be a microbiome, a lot of bacteria present within the storage site. And we can see that basically the type of bacteria is highly relevant for what type of impurities can potentially be produced. But we have three main processes that are well known in the literature. So these are the production of methane via methanogenesis. We also have the acetogenesis to produce acetic acid, and then the sulfate reduction to produce hydrogen sulfide. So these kind of reactions can take place in almost any underground storage site, but they are very sensitive to things like the site environment, so the pH, temperature, salinity there, also, of course, the type of rock, the type of bacteria, and finally, the type of cushion gas. So cushion gases are used to allow efficient removal of hydrogen from these types of underground hydrogen storage sites. There are a few common cushion gases, things like methane, CO2, and nitrogen, and as well as just mixing in with the hydrogen, so actually being extracted at the same time. These can also impact the reactions with the sites and with the bacteria. So again, there are a lot of specifics around underground hydrogen storage sites that we don't necessarily have a good overview of how they will impact the hydrogen quality. So we can imagine the types of reaction take place, but we have to investigate each specific site, and we have to figure out also what the concentration of impurities will be after a given amount of time in a storage site. And I don't think that that's something that has been really investigated so much until now. So to kind of very quickly summarize what we found about the different sources of impurities, we looked into hydrogen production, hydrogen storage, and transmission, and we found that there were several key impurities that were common across the entire value chain. So several impurities, for instance, nitrogen, oxygen, CO2, these are things that are involved in both production, also transmission and storage. And in particularly, if we want kind of large scale implementation of hydrogen, then there's going to be storage underground in depleted reservoirs and also transmission in gas pipelines. And this can really introduce a lot of different hydrocarbons into the hydrogen. So when we try and define our industrial quality standard, although we might not know exactly the concentration of these impurities that will be introduced at each stage, we have to make sure that these are well represented in the standard so that we can really, try and monitor them and try and understand what the progression of these types of impurities are over time. So just a final word on the impact of fuel cells. This is obviously a key topic of the Cleaner project, so I wanted to just talk about it a little bit. But as you saw in the very beginning, low temperature fuel cells have a quite strict quality requirement. They would require quality of 99.97% purity, which is going to be quite expensive. So one of the key aims is that if we can operate fuel cells with a lower quality hydrogen, it can lead to the wider implementation of fuel cells because it reduces the kind of operational costs. But in order to actually be able to operate with the lower quality, we need to understand the different mechanisms for performance loss in the fuel cells. And this is obviously dependent on the different types of impurities present. So certain impurities, for instance, CO and H2S, can absorb directly onto the catalyst layer and block the hydrogen oxidation reaction. Other impurities can actually integrate into the membrane and replace these protons that are moving across. These can be things like ammonia, and also different transition metal cations can do this. And finally, we can also just get a simple dilution of hydrogen with more inert impurities like nitrogen, argon, and also methane. So there are several different methods that impurities can impact the performance. Again, one of the main goals of the project is to actually understand these and try and figure out how we can then mitigate them, either by making new materials. So for instance, we can design new catalyst layers that reduce the absorption of these impurities, or we can try and figure out different operating methods to reduce the dilution of hydrogen and increase the efficiency overall. So those are the key aims of the project. The project, I think Anders mentioned, has been going for just over a year now, and it's a 4-year project in total. So I just wish you all to keep updated, keep on track, and just we'll be producing a lot of new innovations, hopefully, going forward. So yes, final conclusions of my part of the talk are that impurities can be introduced at all points of the value chain. The production is relatively well controlled and well understood, so we can couple these different purification techniques to the production processes and have a good control of our quality. But as soon as we put it into, for instance, a repurposed pipeline or an underground storage site, there becomes a lot more open questions about both the types, the concentrations, and the lifetime of these impurities. So one of the key points is that actually monitoring hydrogen quality is really important, because we need to actually keep track of what's introduced into the hydrogen, so we know that we need to remove it. And finally, there are a lot of open questions about the industrial hydrogen quality. I don't think I necessarily answered the question of this talk, which is what is industrial quality hydrogen, because there are still open questions around, first of all, the standard itself. So should it be 98, 99.5, or 99.97% purity? I think the most likely would be slightly towards the lower end here, maybe around 98% would be suitable for several applications. But the question also is, who should be responsible for maintaining this standard? This is not something that can be answered by me. This is something that obviously the gas distributors, the producers, and the end users all need to come together to try and understand. So yes, a lot of open questions still here. But yes, thank you for listening. Thank you for joining our presentation today. I want to next just move directly on to the panel discussion. So hopefully our panelists can turn on their cameras, and yeah, there you all are. And I would like to just ask you all to kind of one by one introduce yourselves, give us a little talk about your background, whilst hopefully some of the audience members today can write some questions for you in the meeting chat. So first of all, I think Thomas, well, we have two Thomases today. So Thomas Storr from HyCenter, maybe you can start introducing yourself.
Thank you, Kathy, for the nice presentation and also for the invitation to join the panel discussion here. My name is Thomas Storr, and I'm researcher and project manager at the Hydrogen Research Center HyCent in Austria. And with my research group, I'm focusing on hydrogen quality analysis and quality monitoring. And therefore, we've also been able to make an investigation on the hydrogen quality in used natural gas pipelines. Thank you, Katie, for mentioning it.
Yes.
Looking forward to our discussion.
Perfect. All right, then we can hop over to Thomas Bird.
I'm Thomas Bird. I'm the Senior Engineer for Gas Quality at National Gas. So currently we transport natural gas around the UK at transmission pressures, but we are keeping an eye on the future as to what that will look like in terms of hydrogen blends and 100% hydrogen. Thank you for the invitation and the presentation, Katie. It was really good.
Great, thanks. Then next up we have Felix Haberl from Volvo.
Hello, Felix Haberl, propulsion concept engineer here at Volvo at Powertrain Strategic Development. So we're a small department developing future powertrains, currently focusing a lot on the fuel cell powertrain for our truck applications. Fuel cells coming from our joint venture. So they developed that cell-centric, so same fuel cell used by Daimler Trucks and us. And firstly working with some fuel cell research related questions and hydrogen storage on the vehicle. Nice to be here.
Great, and then last but not least, we have Remco from TNO.
Yes, hello everyone. My name is Remco Groenenberg. I lead the R&D program on underground hydrogen storage here at TNO. TNO is the Netherlands Organization for Applied Scientific Research. We're actually quite comparable to SINTEF in that way. So I've been with TNO for 6 years. I'm a geologist by background, so focusing on the subsurface all my career. And at TNO we have a program, an R&D program that focuses on the storage of hydrogen in salt caverns and reservoirs. Also coordinated large European research project, HyESPRIT. You already mentioned it, Katie, and also a number of nationally funded research and development programs on this topic, and currently also involved in a demonstration of hydrogen storage in a reservoir in Austria under coordination of RAG, the storage operator, natural gas storage operator. It's called the EU H2 Stars project, but I can say a few more words about that in the panel. Thanks for inviting me, Katie.
Yes, perfect. So thank you all for being here. Just as an introduction kind of to the concept of the panel was that we wanted to get different actors from, again, throughout the value chain. So we have, of course, some end users, we have some people who are interested in hydrogen transmission, and also Remco is interested in hydrogen storage. So maybe it's a bit cheeky to start off with what I think is the most difficult question for our panelists, but it's something that I brought up at the end of the discussion there, which is when we think about hydrogen quality throughout the value chain, who actually do we think should be the most responsible for ensuring the hydrogen quality? So does anyone want to jump in with an opinion there? Maybe your opinions might be different from one another. But yes, how about, Remco, please go ahead.
Let me volunteer here. No, I think actually responsible for the quality, I would say there is a logical party that could be responsible for that has the best position to make sure that the quality actually meets the specifications, right? I guess the specifications would have to be agreed on on even European level, or on the level where all the countries that have a hydrogen grid are actually attached to that grid, right? But I think that the natural place to administer the quality is entering the gas grid, right? And that's where the TSOs, the transmission system operators for the gas grid, come in to make sure that the hydrogen that is produced or injected, I should say more injected into the network, actually meets the specifications. And then who actually sets the specifications? That is, I would say, ultimately it should be decided on European level, I think, unless we want to have a system where at every boundary between two countries you will have to, you have to switch between qualities. I think that's impractical, right? So that's just my 2 cents. I think it should be a national or even European agreement on quality, and then the party to administer that would be it would be the TSOs to make sure that that quality is actually met. Yeah.
Yes, nice. Thomas, you have your hand up, so maybe you have some comments about that as a TSO yourself.
Yeah, I think on that one, it probably comes down to sort of a cost-benefit analysis and sort of an economics question. As a TSO, we don't tend to do purification ourselves of natural gas. We rely on the delivery facility operators to ensure that it meets the specification, and we just check that quality. But I do agree with what you're saying. We need some form of universal approach to what the quality should be across Europe, because, as you say, we don't want to be changing qualities between different countries at interconnectors and so forth.
Yeah, indeed, that was also my proposal. Indeed, that I mean, the TSO is not the party that purifies, right? But it just checks that the quality upon entering the gas grid is actually met the specifications. So that's
Yeah, but I think this is interesting because, of course, now I'd like to bring in Thomas Stohr, who did some very interesting research that showed that actually what goes into the grid might not exactly be the same as what comes out the grid. So what's your perspective on how that needs to be managed?
Exactly. So I think the first and major issue of what is the preparation of the pipes itself. So in our investigations, we saw that the main source of impurity for impurities are the residues that remain within the pipe, and therefore we think that flushing with nitrogen and pigging will be a very crucial part for raising the hydrogen quality, especially at the beginning of the transition process itself. And this is also the measurements that will have the most impact on the hydrogen purity itself. So I think a common sense about how the refurbishment and of the pipes itself will help a lot to raise the quality within a pan-European network.
Exactly. So this is something that maybe needs to be monitored continuously so we know and understand how it develops. So Thomas Bird, maybe I can go to you. Is this something that you're actively monitoring at the moment, the quality of the hydrogen or the gases going in and out of the pipelines? And do you see that the existing monitoring standards that are used for natural gas can then be easily transferred to hydrogen in the future?
Yeah, so currently we don't transport 100% hydrogen, although we do have our test facility that's at Spade Adam in Cumbria. So they have gone up to 100% hydrogen, though this was mainly for sort of mechanical testing of the system, the repurposed assets that they have there. And unfortunately, when they did those tests at 100%, they didn't have the gas analyzer operational, so they weren't able to test that the gas they got out was 100% or what percentage that is. So we do have another further piece of work to do some tests on a variety of sensors to see what the specification of hydrogen that comes out of that is. And we will be sort of pushing hard to ensure that that research gets done.
Yes, perfect.
And then, sorry, on the second part of your question, yes, I agree that we should be monitoring the quality of the gas going in. Some technologies would be able to be transferred, such as tunable diode laser absorption for some components like moisture in the gas, but others will require sort of brand new assets or modifications to existing assets.
Perfect, thank you. Then I wanted to jump over to Felix. So we haven't heard from you, but there are certain people that maybe think that the end users are the ones that should be responsible for purification because, of course, you have the standards that you need to be met. So is this something that you as an end user would be willing to do in the future? Get low quality hydrogen and then purify it yourself?
I mean, maybe for clarification reasons, we would be the ones that kind of specify the quality that our vehicles need to be used with. And then we're Volvo as a company, not active in the value chain, at least for now, in distributing and dispensing hydrogen. So we would put the requirements on the nozzle for our products. But I definitely think that there's the possibility that our infrastructure partners, like the operators of the refueling stations, that they might use purification equipment close to or within their supply chain to the refueling station to ensure the qualities that we are requesting for vehicles to be used.
Yeah, so this is interesting because I guess, like you say, you would set the quality standards. So currently that's 99.97%. But do you see that in the future there would be a demand for fuel cells to be able to utilize a lower quality hydrogen, maybe for economic reasons?
Yeah, exactly. I think you pointed out the total cost of ownership is the important argument for selling our vehicles. And there's also the reason why we haven't really seen this incline in hydrogen-powered vehicles yet, because the economics are just tricky. So total cost of ownership is to a large extent dominated by the fuel cost at our customer side. So if there are possibilities to reduce that major part for our customers, then we're increasing the competitiveness of our products. So there needs to be a good understanding and a good cooperation between what kind of cost can be reduced on the infrastructure side if we have another quality of fuel to our products. At the same time, a lifetime is really important. We're designing for 25,000 hours. So we really need to ensure just the lifetime of the product, and that has been done or is done with a specific hydrogen quality. So if that quality is changed, then there is quite a lengthy, complicated and costly recertification, reevaluation process required. So I think it's kind of this interaction between the OEMs, the fuel cell manufacturers, and the infrastructure that's really important to kind of get this optimized, I would call it optimized, quality and total cost of ownership perspective.
Yeah, exactly. And like you said, the TCO is dependent on both the operational cost and also things like the fuel cell cost and lifetime. So there is a balance there that needs to be investigated. Okay, but I think maybe I would like to go back to Remco, because in my presentation there were quite a lot of open questions about underground hydrogen storage. So maybe you can give a little overview of what your projects have found with respect to the feasibility, first of all, of underground hydrogen storage. And then secondly, do you have any words about hydrogen quality and whether you've done any experiments on that aspect of things?
Yeah, of course. So HyESPRI researched the techno-economic feasibility and potential for storing hydrogen in porous reservoirs, so depleted gas fields and aquifers in Europe. And one of the key aims of HyESPRI was to better understand the key processes and risks associated with storing hydrogen in those structures. And there, through an extensive set of laboratory experiments, the consortium investigated more fundamentally the geochemical, geomechanical, microbiological, and flow transport processes, so to say, in porous reservoirs in the presence of hydrogen. And we actually focused on understanding and minimizing the risks associated with reactions and interactions of rocks and fluids and microbes in reservoirs, and the durability and integrity of reservoir rock, cap rocks, and so basically making sure that the hydrogen stays contained in the storage. And we did not really identify any showstoppers, and that's important to mention. And then for implementation, and as such, the results can be considered encouraging. Also for storage of hydrogen in reservoirs, which is actually not yet done commercially anywhere in the world. Of course, storage in salt caverns is done commercially at several places in the US and in the UK, also in Teesside since the 70s, and albeit for a different purpose, just backup for petrochemical complexes rather than balancing the energy system of the future, so to say, right? And I think what is important to mention there is that when it comes to the expected purity of hydrogen upon withdrawal from the storage, then there is a difference between salt cavern storage and storage in reservoirs. You mentioned it already, yeah. Of course, in reservoirs, there is, at least in depleted gas fields, let's say it like that, there is residual natural gas always present, right, in greater or lesser amount, depending on the depletion state. And this will inevitably come back with the hydrogen upon withdrawal and needs to be separated, right? And of course, natural gas contains a number of compounds, right? You mentioned that already. So and this purification requirement for storage in reservoirs adds to the cost. Basically, it's not a showstopper. It can be dealt with, and we know how to do that. It's more that it just costs money, right? And there, yeah, that's a key difference. I mean, storage in salt caverns. I think the thought currently, the common sense is that you need to how shall I say that, dehydrate the hydrogen. You need to dry it upon withdrawal. The expected level of contamination is going to be probably quite minimal, and it will probably take much less effort and cost to bring it back to the spec. Although having said that, 99.997, that's really high. So I guess you could argue, I mean, of course, from the salt cavern storage, it goes back into the pipeline. So I would say the point where this would be measured from the perspective of storage is to meet the quality spec of the grid, right? So and that storage would need to purify or dehydrate or whatever to bring it back to the quality spec of the grid.
So then it sounds like it's highly feasible for us to have salt caverns that are kind of with one additional purification step and then going back into the grid at maybe 98 or 99.5% purity. This is highly feasible for...
Yeah, for salt caverns and reservoirs as well, actually, of course. But then for reservoirs, it will take more effort and more cost, right? I mean, of course, you can still purify to that level. It will just be more costly, and this is actually also so therefore the evolution of the hydrogen upon storing it, right, and the level of mixing with the cushion gas in the reservoir, which I think natural gas is pretty much considered, well, the standard is not the right word, but it's the most logical option, right? The other ones you mentioned are really exotic, and of course they're in the research domain, but I wouldn't call them common. CO2, nitrogen, but it's clear that you will need to do more when storing hydrogen in a reservoir in terms of purification than when storing it in a cavern. And we have this EOH2STARS project in Austria that is really demonstrating hydrogen storage in a gas field, a small gas field, and will also measure the evolution of quality upon withdrawal over 4 yearly cycles in sequence. So then we can see what happens to the hydrogen when stored over multi-cycles, right? And is there a sort of self-cleaning, self-purification in the storage, right? Because you, of course, also produce these contaminants and you produce the residual natural gas. You have to replace it with hydrogen then, right, as a cushion gas. But you clean the store over time. That's the thought. So this is definitely something that is currently high on the research and demonstration agenda. Yeah.
Perfect. Well, it's very encouraging that you have these kind of research projects ongoing, and particularly, like you say, the sequential charging and discharging is going to be really interesting to follow into the future. So I'm looking forward to seeing some results for that one.
Thank you.
Okay, but now we don't have too many minutes left, so I'm wondering, Anders, if there have been any questions from the audience that you would like for us to bring up now?
Yeah. I have tried to answer some of them, but those are more specifically related to the project. So I think what's still open here is a question from Christian Spitta, ZBT, on a German opinion or suggestion on sort of defining one quality standard for in and outlet. I'm guessing that's on pipeline hydrogen, or if it's more specific, perhaps you can comment again in the chat, Christian. But any comments on sort of different standards for in and outlet of systems or storages or transmission solutions?
Yeah, I think that's quite an interesting approach to have one standard for entry and a standard for exit. As Katie's slide 15 showed, there's a lot of impurities that to do with the sort of age of the pipeline, they're increased. And also, if you consider the sort of length that would of the pipeline that it's got to go through, that could increase the lifetime of these impurities because it's a much bigger surface area, and so some of those impurities could hang around for a long time. So I think yeah, it's definitely something that could be considered.
Yeah, because I think it's interesting also in this future European hydrogen backbone about the integration of the old and the new pipelines. So there's also the potential that the old pipelines can go ahead and actually contaminate the new pipelines with some of these impurities if they are downstream. So do we have any thoughts about that? Thomas Stöhr, I see you just put your hand up, so maybe you have a comment.
Yes, I want somehow to, well, not to discriminate the older pipelines, because what we saw in our investigations, and we really made experimental setup from real pipelines that we excavated and filled up with pure hydrogen. We saw that the impurities that enter, that with our investigations, we saw the direct influence of the pipe itself on the hydrogen. And therefore, all the pipelines, yes, they have a contamination potential, but they are, in a worst case scenario, we have on a very low level, on PPP level, we saw some contaminations, for example. But there's one other aspect that is neglected now in these discussions as well. These are the compressors and the compressor stations, because the grid does not exist from the pipes alone. There are also compressor stations and so on, and this will also have a major impact on the hydrogen quality itself. That's something just from our perspective now that has to be considered as well for the discussions. And here we have very less experience on that.
Yeah, no, it's a very good point. I mean, the entire pipeline system, including the, things like the cleaning and the stations, both the transmission and also the distribution networks need to be taken into account completely.
Exactly.
So yeah, lots of open questions, but lots of interesting scope for discussion there. But unfortunately, we are at the end of our time now. So I would just like to thank everyone for joining. Thank you in particular for the panelists for a very interesting discussion that I, could go on for several hours. But yeah, lots of interesting points and perspectives. So thank you all for joining.
And also thanks to you, Katie.
Yep.
Thanks, Katie.
Thanks, everybody. Have a nice day.
Thank you.
Thank you, everyone.
Have a nice day. My pleasure.
Bye-bye.
Bye.